Hi everybody, in this video I'm going to walk you through activity 5.7. This is problem 9A currently in the curriculum, and what we're trying to figure out is if we have a box here that weighs 100 pounds, what force would be required to tip it over? If I'm applying it where the green arrow is, that would be at arrow T, right? Force T. We're going to assume here that the box tips over around point P. That's kind of my rotation point, my fulcrum, if you want to think about it that way. We're going to assume that the box does not slide. So here's how we look at this problem. This is really a simple machines problem. It's a levers problem if you want to think about it that way. We have two forces that are acting here. We have the force that wants to tip it over, T, and if that force was applied and it rotated, you would notice here that we could apply this force, right, and it would rotate it this way. Okay, so we have a counterclockwise rotation. I'm going to put CCW for that. Okay, if that was the only force that was applied, this thing would rotate counterclockwise, but something is counteracting that, okay, and that is the weight of the box. And so if we think of the weight of the box, now obviously this is sitting on the ground or something, okay, but if we ignore that for a second, just thought, what about this box here? You know, what if it was just rotating here? That force would be counteracting and going clockwise. So we have a counterclockwise force. That would be a counterclockwise moment, is what we call that. A moment is a way of saying a rotational force. A counterclockwise moment and a clockwise moment, and those are counteracting each other. So what I can do mathematically is I can say that the counterclockwise moment and the clockwise moment are equal to each other. Okay? That's what I'm trying to figure out. So the question then becomes, how do I figure out the moment? How do I figure out the counterclockwise and clockwise moments and see how those are set equal to each other? Well, it turns out that the formula is just force times perpendicular distance. So that's kind of the key on all of this stuff here, is that we have a moment, we'll call it M for moment, is equal to force times a perpendicular distance. Turns out that this is way simpler than it looks. So what I have, let's do the red ones on the left, okay? What I have is the weight of the box is applying a moment. That's a force. And the force in this case is 100 pounds, right? The box weighs 100 pounds. So if I take then a 100-pound force and I'd apply it at a perpendicular distance, so what I'm interested in is the 90-degree distance from here to here. I'm drawing it just above so you can see the red, okay? But I have a distance of 1 foot in this case. A 100-pound force, 90-degree angle distance would be 1 foot to the perpendicular, or to the point of rotation. So I'm going to take 100 times 1, and that will give me then the clockwise moment. So then what's counteracting it then would be the tipping force that I'm applying. So I have a force that's applied this way, and if I look at the perpendicular distance, I'm going to draw it next to it, we can see here that that is clearly the 2-foot mark, right? So I have a force of T pounds that's being applied at a distance of 2 feet. And it turns out, look at this, I have an equation now where I can set these two things equal to each other, and the only one I don't know is T. So you know what, let's divide out the 2 then. Let's divide both sides by 2. What is 100 times 1 divided by 2? And it turns out that the tipping force in this case is 50 pounds of force would be required to tip that box over. That's long and short, that's every single tipping force problem in a nutshell. We have a clockwise and a counterclockwise that counteract each other. We do force times distance and set those equal to each other. A force times a distance is equal to a force times a distance, and then we solve for the thing that is unknown. Hopefully that makes sense. I'll be doing more videos here in a few minutes over the remainder of the problems from activity 5.7.